One more step, then we can do conservation of energy. The step is to talk about conservative versus non-conservative forces. So I am going to show you a YouTube video. This is a demonstration of conservative and non-conservative forces. The conservative force we're going to look at is gravity, and the non-conservative force that we will look at is kinetic friction. A conservative force does no work while the object executes a closed path. So for example, if I start with this block here, and this is my starting point, I go horizontally, vertically, over, and back down, with my ending point being my starting point, I've executed a closed path with this object. Let's look at the work done by gravity in moving through this square-shaped path. As the block moves from here to here along the table, it's moving horizontally, but gravity acts vertically. And so the displacement of the object and the force itself that we're considering the work for, namely gravity, are perpendicular to each other, and that force of gravity does no work if the displacement and the force are perpendicular to each other. Now when gravity, as the block goes vertically for this leg of the square, the displacement is up, gravity is down. And when the displacement is in a direction that's opposite gravity, then the work done by gravity is negative. So we got zero work here, a negative amount of work here. Then we're going to move along the top edge of this square. While we're moving horizontally, gravity is vertical, the displacement is horizontal, the work done is zero. And then finally, the simplest possible case is where I go from this corner back down to my starting point again. In this case, the displacement is vertically downward. That's in the same direction as gravity. And when the force and the displacement are in the same direction, the work done by that force is positive. So we've done zero work here, negative work here, zero work here, and positive work here. And the positive amount of work done on this side exactly cancels out the negative amount of work done on that side. So the net effect is that the net amount of work done by gravity as this block executes this closed path is zero. That's what we mean by a conservative force. So let's look at the case of friction. Kinetic friction acts in a direction that's opposite the displacement. So I'm going to imagine doing a square on the table's surface here, 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 and here, coming back to my starting point again, and I'm going to ask what the work done by kinetic friction is. As I go from here to here, the displacement is in this direction, but the kinetic friction is opposite that displacement. So the work done by the kinetic friction in that case is negative. As I do this leg of the square, the displacement is in this, and the velocity are in this direction. The kinetic friction opposes that displacement. It's in this direction. So again, the work done is negative because the displacement and the force are opposite each other. What about this leg? The displacement is in that direction, kinetic friction in the opposite direction, again a negative amount of work. And then finally here, displacement toward me, away from you, and kinetic friction toward you, they're opposite again, you get a negative amount of work. So each one of these legs of this closed path that this block is going through, kinetic friction does a negative amount of work. So none of those are going to cancel each other, and you're just going to get 4 times that negative amount of work for each one of the legs of the square. So kinetic friction is not a conservative force because the work that it does in executing a closed path is not zero. In this case, it's negative. Okay, Good introduction to the idea of conservative forces. We're going to give two versions of the definition of a conservative force, one which was discussed in the demo video, and the other that was not discussed in the demo video. The one that we talked about in the demo video is this one. A force is conservative when it does no work on an object that executes a closed path, meaning that it starts and finishes at the same point. So for the example here, for the roller coaster ride, if there is a force that does zero work while this coaster executes the complete circuit and comes back to its starting point, its starting point and its ending point are in the same place. If there's a force that does no work during that whole closed path, then that force is conservative. Is there such a force? And the answer is yes. Gravity. So gravity is conservative. That is, gravity is a conservative force. It does no work, as we showed in the demo video, that a negative part here and a positive part here, and they cancel each other out. Gravity is conservative. It does no work. W-O-R-K on an object that executes a closed path. All right. A force is non-conservative when it does some work on an object. So a force is conservative if it does no work. The work is zero. But it's non-conservative if it does some work. Friction is an example of that, like we saw in the video. It does a negative amount of work. Here's the other version, and these two versions are actually equivalent to each other. One can be proved from the other one. A force is conservative when the work it does on an object is independent of the path between its initial and final positions. So if that work done is independent of the initial and final positions, then the force is conservative. We know that for gravity because gravity is going to do no work independent of the path we take between the starting point and getting back to the starting point. We could have a coaster that just comes down here and it comes right back up here. It's a different path. It would still do no work. And so that's true for this particular case, but in this actually version of it, the initial and the final positions don't have to be in the same place. So we could have an initial position here and a final position here, and we could take a nice straight line path between the initial and the final position, or we could take a windy one, and the work done by that force between those two positions would be the same. One example of that for gravity is that we talked about the basketball just dropping straight versus the basketball going up at an angle and coming down. As long as the initial and final heights were the same, the work done ended up being the same, because the potential energy and the work depend only on the initial and final heights. That's the reason. All right, which forces are conservative? Gravity, talked about that. Elastic spring force, the force of a spring on an object, is approximately conservative. We'll talk about that in Chapter 10. The electric force is also conservative. We'll talk about that next semester. Non-conservative forces. Kinetic friction, we already talked about that one. Static friction is another non-conservative force. Air resistance is non-conservative. Tension is non-conservative. Normal force is non-conservative. and the propulsion force of a rocket, non-conservative. All these forces, if you execute a closed path and come back to your starting point, you will have done some amount of work, either positive or negative. The normal force, for example, this pen lying on my hand, if I consider the work done by the normal force and going up, then the displacement is up, the normal force is up, the amount of work done by that normal force is positive. And if I come back down again, well, that's actually an example where the normal force is conservative. The normal force is still up, the displacement is down. There are cases, can't think of one right now, where the normal force is non-conservative, and the tension, etc. I have to think about that a little bit more. Complete the following statement. In situations involving non-conservative external forces, the work done by these forces can be either positive or negative. That's certainly true. The work done is always equal to 0. That's not true. Work is not necessarily always positive. It could be negative or positive. Usually cannot be determined. So they can be either positive or negative. Think about that normal force example. I'll think about it a little bit more as we go on.